DDR, that's the interface. And then let's look at the history of the DRAM. And the DRAM concept was proposed by Robert Dennard, and this is an IBM fellow. And in 1966, he is also the one who proposed the Dennard scaling rule, and he is a very famous guy. And then in 1970s, the first DRAM chip with 1T1C was fabricated. And at that time, you can see the capacity is only 4 kilobits, and the VDD is like 12 volts, and the access time 300 nanoseconds, and the refresh time 2 milliseconds. So today we improve those a lot. This is from 1970s. So the DRAM scaling, we look at the minimal feature size, and as we discussed before, the DRAM and the flash, the feature size F is more related to the physical dimension, like the metal one half pitch. So this is the scaling of the DRAM from the 1990s to today. And today's DRAM, the F is below 20 nanometer. So somewhere maybe 15 or 14 nanometer these days. Above 10, but below 20. And the companies don't disclose what is the exact number, so they use 1X, 1Y, 1Z generation to represent the DRAM node. And for DRAM product, actually there are different kinds of DRAM product available in the market. And this is depends on applications. So the first is the main memory. This is the most common situation. And we have those DDR 1, 2, 3, 4. And these days we don't say DDR 1 and 2, so mostly 3 and 4 these days. And then the second one is the mobile DRAM. This is for your phone. So if you look at your phone spec, it will be LPDDR3 or LPDDR4 these days. So LP is no power. And then the last category is graphic DRAM. This is for high performance computing or the gaming business. So then we have this standard called GDDR3 or GDDR5, or this days I think there will be GDDR6. So this is graphic DDR. And there are some subtle differences, and I will not go into the details of the table. Of course, with the more advanced generations, the power supply is decreasing, but the data rate keeps increasing. So here is the BPS, bit per second. And you can see the like DDR4, 3.2 giga BPS. And of course, if you look at the GDDR, then it's much higher and much more power hungry for the gaming. So I will not go into the details of this table. So basically 3 types of the DRAM. And the first one is this main memory, or sometimes people call it a commodity DRAM. So this is the most common for your laptop or for the workstation. So this is the most common ones. And for this type of DRAM, so the priority is to optimize for the cost. Low cost is the priority. So if low cost is a priority, then the design will look for large segment. That means large match. That means the bit line as long as possible, word line as long as possible. But of course, those will be limited by something, right? For example, the bit line will be limited by the signal in the sensor amplifier. We will talk about this later. So it's limited by the delta V, the voltage margin you can sense. And the word line is limited by the row timing because you have the word line pulse, and then this pulse needs to propagate through the word line. Then for the last column, then you need to satisfy the timing requirement. If the word line is too long, then there will be too much delay. So, and here this is just an image for the commodity DRAM, and at a 38 nanometer node. This is at 2012. And the second type is the mobile DRAM, and in this case, your priority will be the low power. So you need to optimize for the low power. And if you want to reduce the power, then for the refresh, you need to make it the interval between the refresh as long as possible. And then the leakage current should be as low as possible. So this low power is a key feature for the mobile DRAM. And some moderate cost is acceptable. If you need to engineer for the low power, you may have to sacrifice some of the density. So, but this is acceptable. And the graphics DRAM, of course, is performance driven. And here you don't care about the cost because you are willing to pay for that. And in this case, so the short bit line, short word line, because you want the latency to be small. So then you need to shorten the word line or bit lines to reduce the RC delay. And then this is a very high performance and high energy and high cost. And this is a trend for the DRAM product. And here this is the data rate. It's in gigabit per second per pin. And here we have DDR4. Here is DDR4, and the LPDDR4, and this is the GDDR5X. So it's already more than 10 gigabit per second. And then this is also the same trend, but this one shows the supply voltage, VDD, decrease with the generations. And one more chart showing the data rate. And here again, the GDDR5 more than 10 gigabits per second. So this is the general trend for the DRAM industry. So any questions? And the DRAM market share. So actually only 3 major companies are producing DRAM these days. And here, number 1 Samsung, number 2 SK Hynix, and number 3 Micron. And those 3 will occupy more than 90% of the market of the DRAM. So this is quite dominated market. Okay, so those are some non-technical informations for you. And next, we are going to have more technical discussions on the DRAM cell operation. And you need to understand how the DRAM is read out, and what is the timing, and what is the sense margin. So DRAM is this 1T1C, and here we show some of the schematic for the DRAM cell. So DRAM cell is this 1T1 cell. You have 1 transistor, 1 capacitor. Okay, and the transistor's gate is controlled by the word line, and the transistor's source and drain doesn't matter. So let's say one terminal is connected to the bit line, and the other side is connected to the capacitor. And the capacitor's other electrode is connected to so-called the common plate line sometimes called. And if you look at this, the circuit schematic is very simple: one transistor, one capacitor. But actually, on the chip, the 1T1C structure is quite complicated. It's not as simple as you may think. So here, this is the schematic for this 1T1C. So can you say where is the T, where is the C? Any idea? So transistor is the substrate here somewhere. So the transistor, this is the transistor. And let's say this is a transistor. So here is the gate, and the gate will be controlled by the word line. And then the transistor source and drain. One side is connected to the bit line contact. The other side will go to the capacitor. And this SN is storage node, where we store the data, where we store the charge. And then the capacitor is here. Okay, we have a very tall cylinder kind of capacitor there. So this capacitor, if you look at it closely, so it's actually something like this. So this is one electrode, and this is this plate. And then here the other side, the other interface is connected to the transistor. This is a storage node. So here this is the DRAM cell, and then on the edge we have this peripheral circuits like the sense amp or the word line decoder. So those are different transistors as well, as you can see here. So any questions? So let's look at some of the real images here. So again, the left-hand side is this schematic, and the right-hand side is the real reverse engineered Samsung 20 nanometer class DRAM under the TEM, the microscope. And can you see where is the DRAM transistor and DRAM capacitor? So it's here. This is similar as the schematic. So here we have this DRAM capacitor and the DRAM transistor here. This is T and this is C. And then this side is peripheral circuits. And this is a contact to some of the peripheral circuits. And you need to route on top of this capacitor, because this routing you cannot pass through here. The metal line, if you want to route some sense amp to some outside, then you have to go to very top, and then you have metal here to go over the DRAM memory array here. So let's have a closer look at the DRAM cell. This one T1C, and here we have two microscope images from the TEM. So this is a side view, and the bottom one is the top view, more like a layout. So here from the side view, this is the transistor word line, which in this side view is in and out of the plane. So you have the word line in and out of this plane. And bit line is here, which is perpendicular to the word line, because word line is in and out of the plane. And then this is a transistor, And then transistor 1, let's say source or drains connect to the bit line, and the other one connect to this capacitor here. From the top view here, this is the word line, and this is the bit line, and then here is the transistor, and this is the cell. Sorry, this is the contact from the transistor to the bit line, and then the capacitor is somewhere here. And here, this is a circuit schematic. We have the word line, bit line, and the capacitor. And this is a storage node. We store charges here. If you have charges here, then you store 1. If you don't have charge there, you store 0. So this is the storage node. And the other one is a common plate. And here the capacitance CS. Okay, so this is a DRAM cell structure, and then we need to understand how we can sense the data from the DRAM. So as I said, so if you store 1, that means the storage node stores the charge, and then the node voltage is VDD. And if you store 0, then you don't have charge in the storage node, then that node voltage is ground. So let's look at this timing diagram. So typically, this is for read operation. Before you turn on the word line, if you want to read the data from that particular DRAM cell, you need to pre-charge the bit line to be half VDD. And then we turn on the word line here. This one. We turn on the word line. So let's assume that the cell stores 1. So that means the storage node is VDD. So after you turn on the word line, then the current will flow, because your storage node stores 1 is VDD, and your bit line is half VDD. So that means your storage node will have higher potential than the bit line, so current will flow, or charge will be shared. So we can understand this through this simple circuits. So this is the switch, essentially is this transistor. And on one side, this is your storage node, and this is the cell capacitance CS. And here, for example, we store 1, so it's VDD. And the other side is the bit line, and we pre-charge bit line to be half VDD. And we know bit line will have the parasitic capacitance, which is CBL. So this is a simple circuit. And we want to understand the change of the bit line voltage after you turn on the word line. That means after you turn on this transistor. So initially the bit line voltage is half VDD, but after you turn on the word line, the bit line voltage will become half VDD plus some voltage. Because in this case, this is VDD, this is half VDD, and then current will flow this way. So that means the charge is transferred. So then you are going to charging the bit line cap, so the bit line voltage will increase by delta V. So we want to know what is this delta V, because that is the sense margin. So what you can do here is to use the charge conservation, because no matter you turn on or turn off this switch, charge will be conserved. So before you turn on the word line, if you look at the charges on the cell capacitance, that will be Cs times VDD. That's the charge here. And then on the other side, is this CB or CBL, the bit line capacitance, times the bit line voltage is half VDD. So that's the total charge before you turn on the word line. And after you turn on the word line, eventually, so the current will flow and charge will be shared, and eventually, current will not flow, will stop flowing when the Vs equals to the VBL. If they have the same potential, then the current will stop flowing. So that means this VBL prime or VBL new will have the same potential here and here. So then the charge will be Cs times VBL prime and CB times VBL prime. This VBL prime is the new VBL after the word line is turned on. So you can solve for this VBL prime here. You can solve for that and minus the VBL, let's say the new and the old. The old VBL is half VDD. And the new one will be half VDD plus some delta V. And you can solve for this delta V. If you do that, then this is the solution. So basically you just rearrange those terms. I will skip that. And from this equation, you solve for this VBL prime, and then use VBL prime minus the initial half VDD. Then you get this equation. So this is a sense margin, and this is important when designing the DRAM. And we want large sense margin. So here from this equation, if we want to have large sense margin, then what can you do here? So of course you can use larger VDD, but this will cost more power. So this is not desired. So here you look at this ratio is important. CB over CL, that is bit line capacitance over the cell capacitance. You want this one to be small. Or in other words, you want the cell capacitance larger than the bit line capacitance. Again, this bit line capacitance is parasitic capacitance. It's not what you want. Okay. But due to the the wire-to-wire coupling, you have those capacitance. And cell capacitance is what you designed for. Okay, you need this Cs to store the charge for the DRAM. And here we have a variant of this equation. The only difference is here. So if we consider the cell leakage, because the DRAM here is the cap, stores the charge. But capacitor cannot hold the charge forever due to the leakage. So if you consider the leakage current times this time is the refresh time. We will talk about this later. Basically, within this refresh time, you have the leakage current. So the charge that is leaked is this current times the time. And then this charge divided by the Cs is the loss of the voltage in the capacitor, this storage node. So if you consider the leakage, then the sense margin will be even smaller because this node is leaking. That means this node voltage is decaying over time. So if you consider that, then this formula becomes something like this. Okay, then let's go back to this waveform. So let's look at this waveform. So we know this charge sharing process, and after we turn on the word line, so here the storage node is going to decay because current is flowing this way. And then at the same time, this bit line voltage, here this is the bit line voltage. This bit line voltage is going to increase. Okay, and eventually those two will merge. That is the condition here will assume eventually if you have equal potential between the storage node and the bit 9, then the current flow will stop. And this is the delta V we calculated through this equation here. So this is the delta V. So this is a change of the bit 9 voltage, and this is the sense margin. So later, the peripheral circuits, the sense amplifier needs to look at this delta V and then convert this to your output. And in this case, this delta V is positive. Then after the sense amp, you think is 1. In other case, if the storage node stores 0, then you can draw the waveform by yourself. Basically, here will be somewhere something like this. It will decay, and you have delta V negative. Then you can get the data 0 after the sense amp. Okay, so this is charge sharing, and then we'll talk about later this right back. But before we talk about that, we can look at the delay time here. So this charge sharing takes some time. And here we can use a simple RC circuit to estimate the time. And here, for example, we have the transistor's channel resistance, RT. This is the channel resistance of that transistor. And then for this simple circuit, you know this is first order RC circuit, and then you know this kind of equation, and you know the solution for the voltage is something like this. I will skip that. But the most important thing is the time constant is RC. And in this circuit, the only R is this RT. And C, those two capacitors are in series to that R. But you know, capacitors in series, if you get the equivalent capacitance, will be something like that, right? It's 1 over C plus 1 over C, and then the other side is 1 over C equivalent. So you will have that formula here. So this is the RC for this process. And for this, if you want to achieve like 97% of the voltage swing, then you have this coefficient 2.3 in front of the tau. So that is the total delay time for you to get this. And typically this is a few nanoseconds you have to spend this time.